In this project, we are facing a challenging problem which requires us to implement 2 Pac-Man agents that forms a Pac-Man team to win in a food searching competition. The purpose of this video is to present our strategies given advantages and disadvantages in different scenarios, and demonstrate the reasons for the final techniques being chosen, along with some experiment demos. This video is divided into 3 parts: challenge faced, 3 approaches we've taken, and the possible future improvements. There are a few challenges for this project. The first one is the agent must finish computing each action with 1 second, which means the agent should avoid huge computation. Second, the agent should be aware of various possible pitfalls that might happen during a competition and give an instruction for the Pac-Man, such as running into tunnels, deadlock with the enemies, and so on. It means that the agent should be generalized to different situations. The last challenge is the training time is limited, which means the agent should be fast trained. Concerning the above challenges, we realized that heuristic search, MCT, and Q-approximate learning could give us a shorter training time and more generalizable. For the same reasons, we gave up deep Q learning as it requires a long time to train. Besides, the model-based MDP do not suit this project regarding we possess a large state space. We didn't touch classical planning, goal recognition, and game theory due to the time limit as well. Also, through our own competition between agents, we found out that the A-star has the highest win ratio. In the next part, we're going to introduce the 3 approaches one by one.
Let's start with our best approach, A-star. Inspired by the baseline team, we follow the same team structure, an attacker and a defender. Refer to what we have learned in the lecture and illuminated by our first project. We need to clearly identify different goals for Pac-Man under different situations, along with compatible heuristic functions. In a word, the main goal of attacker is to search food, while defender is to defend food. As for the attacker, we added a changing entrance strategy. This demo shows our first version's deadlock issue. Having noticed the issue, we let the attacker change a random entrance when it is stuck for multiple steps. As shown in this demo, the blue Pac-Man changes entrance after stuck for a long time, which looks very smart. In our final version, the 2 major strategies of attacker is changing entrance and chasing after invaders when enemy defender is not nearby. During our implementation, we've made several continuous improvements for the defender. We're changing the wandering defender into a more flexible agent. In the first version, it never ran across the boundary, which is useless when no enemy Pac-Man around. So we let the defender eat food and meanwhile listen to the lost food and go back after food being eaten. In short, the 2 major strategies of our defender is listening lost food and search food when no enemies attacker inside the boundary.
In this project, we have developed a version of agents using the color tracers approach. However, due to the long computation time and model performance, it not adopted in our final submission. The UCT implementation basically contains 4-step selection, expansion, simulation, and backpropagation. In the selection phase, we use Epsilon grading to choose between the best child or random exploration. In the expansion phase, we set the maximum search depth and also a time limited because of the computation time limitation each round. If either of the 2 conditions is achieved, we stop computations and choose the best move for now. During our implementation of the MCT, we have made some continuous improvement. Since before the agent come close to the boundary, the reward propagates back in almost no difference. So it only go back and forth. It takes the agent a long time to reach the boundaries. When color tree search is not efficient in this situation, therefore we simply use plan search before the agent reaches the boundary in this method. However, compared to other methods, MCT's computation is very slow and its performance is unstable. Finally, let me introduce our reinforcement learning approach. We follow the Q values and update formulas that we learned in the lecture, which are shown in this slide. In this part, some features are extracted to calculate the Q values. The agent will choose the action with the highest Q values, and after this action, we could get a reward and use this reward to update the weights. The new weights are stored at the txt files. In the next action, the new weights will be used to calculate the Q values. In this project, we use the socks and the reward to update the weights. However, it could not show the indirect rewards, such as the number of food that the agent carried. The training results are not good enough and the training process is very slow. In order to get better performance, we give some predefined weights to the features so that it could reduce the training time. The problem with our Q-learning is the deadlock issue. We could see that the offender is blocked by the enemy.
Here are some possible future improvements. The most significant one would be making the defender and attacker follow different routes. In our current version, the two agents follows the same path, which is really inefficient. Therefore, separating goal foot for attacker and defender would be necessary. For example, an agent is only responsible for upper foot, while the other is responsible for underfoot.
That's all for our presentation. Thanks for watching.